Hello everyone and welcome on today's video. My name is Wouter Peer and I'm the founder and main developer of GH2 Cloud. And today we will be talking about an important aspect when it comes down to geothermal design, and we've already touched upon it a couple of times, but now we are going to spend an entire video talking about it. And that's namely how one can cope with the imbalance. Now, what is the imbalance exactly? Now, the imbalance is defined as the yearly heating up or cooling down of the ground. And this is basically determined by your building load. So your building has a certain demand for heating and cooling. You pass it over a heat exchanger and a heat pump. And out comes the energy you want to exchange with your ground. So the amount of energy you want to inject in the ground during cooling, and the amount of energy you want to extract from the ground during heating or by the production of sanitary hot water. And this difference is defined as the imbalance. And this imbalance causes a temperature drift in the long term of your borefield. So in this case, our borefield cools down year after year until we reach our minimum design threshold of 0 degrees in the 20th year. Now, there are two sorts of imbalance. And we already touched upon this when we were talking about the borefield quadrants. If you have not watched that video, it's linked in the description. But basically, you have either extraction dominated borefields where the ground cools down year after year, and you have injection dominated borefields where the ground heats up year after year. So either way, they can have a borefield that's limited by our maximum temperature in the long term or by our minimum temperature in the long term. And the reason why you care about this imbalance, about this problem, is because it leads to a higher investment cost. Because in the long term, your borefield has to work for a long time. It's a very expensive component of your HVAC system. So you need to make sure that it can cope with this imbalance. And the higher this imbalance, the more boreholes you need, etc., etc. So it's better to take care of it, to think about it, and to avoid or to cope with it. Because that are basically the two options. And we said the imbalance is determined by your building, but of course your building is designed by architects who make choices about windows, placing screens, shading, the orientation of the windows, the insulation, ventilation, etc. But also the HVAC designers who decide if we're only using geothermal or we're also using air-to-water heat pumps. Do we use active or passive cooling? Which heat pumps we use, modulating or not? Are the heat pumps selected in cascades or not? So this all has a certain influence on the final imbalance, the amount of energy we are exchanging with the ground. So this is what we can do to avoid the imbalance. And what we can do once we have the imbalance is how we can cope with it. And that's exactly the topic of today. So if we have a certain imbalance caused by whatever the design choices, how can we, as a geothermal designer, make our borefield so good as possible in order to make it economically attractive and feasible? And next week, we will be putting on another hat, namely that from the architect of the system designer as a whole. Well, how can we avoid this imbalance? But now let's focus on the geothermal side of things. So when it comes to borefield design, we basically have two time scales. And we talked about this already in the past, so I'm not going to repeat everything. It's linked in the description. But you basically have a long-term effect, how the ground temperature evolves year after year. And we have a short-term effects for the peak powers in the order of magnitude of hours. And both can be important when it comes down to this problem. Now, let me explain that. So when we have the long-term effect, we see this as a yearly temperature drift caused by the difference between heating and cooling, or I should say extraction and injection. And you can see we go from 14 degrees in this case to 12. But we also have the short-term effect because our ground is at around, 7 degrees, and our fluid is at 0 in this case, and it's our fluid that we want to keep within limits. So we have both this long and this short-term effect working together for our design. Now, for the long-term effect, this temperature drift, this was determined by the G functions. How does this ground react in the long term, depending on your configuration, etc. So from this perspective, we know it's always better to put our boreholes as far apart as possible. And this is because the farther the boreholes are apart, the easier it is to exchange this imbalance, this energy, with the what is called the undisturbed ground, the infinite ground around the borefield. And this you can see in the graph here on the left. When you have your green line, your boreholes are 10 meters apart, and you see that your bore field heats up less year after year than in our other two spacings. And this, of course, vice versa, when you have a negative imbalance and your ground cools down, having them further apart will have the lowest influence. They will cool down slower than when they are more closely together. And that's the same also for what's called open configurations. So when you have a line or an L shape or a U shape, this is typically better when dealing with imbalance than if you have a dense or a rectangular shape. Because if you're having a rectangular shape, it's harder for the heat to pass through the boreholes and to exchange it with the surrounding ground. This you can see here. If you have a line, again here the long-term effect is lower because it's easier to exchange energy with the surroundings. So this is rather straightforward, I think. Now for the short-term effect, we were talking about the effective borehole thermal resistance, which tells us something about how good the borehole can exchange energy with the ground around it. And this depends on the single or the W tube, which grout you have, which when you have a laminar or turbulent flow, quite a lot of parameters. We have a whole series about the single and W tube discussion. It's also linked in the description. But the idea here is that with a good borehole thermal resistance, you can actually compensate for quite a lot of imbalance. You can, like a matter of speech, say that they are compensating for each other. Now, what do we mean by that? We have here the figure on the left, where you see that we have a temperature maximum of 15 degrees, and after years we cool it down to 40. And we are limited in the long term by our minimum temperature thresholds. Now you can see here that our short-term effects, the difference between our borehole wall temperature and our fluid, is rather significant. It's from 8 to 2, so it's 6 degrees that we lose there, basically. Now if we would increase our, make our borehole resistance better by decreasing it in value, which you can see on the right, it's the same design, but now our borehole resistance has causes only a temperature of 4 degrees. So we have way more space, let's say, for imbalance. So the lower borehole resistance, the more imbalance our borefield can actually take, because it's easier to exchange the energy with the ground. So that's why we also care about the short-term effect here. Now, something else is whether or not it makes sense to put extra boreholes, because that's also typically something we believe. The more boreholes we have, of course, the easier it is to exchange our energy with the ground. It's a better long-term effect, like our spacing, etc. But the problem is that typically our flow rate through our whole system is determined by the heat pump, and the more boreholes we have, the more boreholes we have to separate our flow into. So more boreholes means a lower flow rate per borehole. And if we take a look at this graph, which we already discussed, I believe almost a year ago, you see that when you have a higher flow rate, a higher Reynolds number, our effective borehole thermal resistance is better. So a better resistance means we can better cope, we can better handle the imbalance, let's say. Now if we drill more boreholes, and we go for an example from 4 to 5, we decrease our flow rate in each borehole by 25%. So we would drop in our Reynolds number, and this would cause our effective borehole thermal resistance to increase, making it harder to exchange energy with the ground. So it is important that when we're playing with the number of boreholes, and whether we're going from 20 to 21 or from 100 to 101, this of course makes less of a difference in the last case. But it's important to keep in mind what the effect on your borehole resistance will be. Because your flow rate does not scale linearly with the number of boreholes. It's determined by your building, by your heat pump, etc. So that's something to keep in mind. And the other option is to drill deeper. Because when we have deeper boreholes, the ground is warmer, because we're closer to the Earth's core. And this means that it's better when we're extraction dominated. So when we have a problem with our minimum temperature on the long term, if we have a higher initial ground temperature, higher undisturbed ground temperature, our lines will actually shift up, making it better to cope with the imbalance. It's not so much that you cope with it, because the curve of your line will not change, but you will shift the lines up, making the borefield more affordable in the end. Now, this only works when you have extraction domination, of course, because when your borefield has a problem with the injection on the long term, the last thing you want to do is to make sure that your borehole is warmer, because then it's harder to inject the heat into the ground. So the borefield approach, when we're working with imbalance, how to cope with it, basically when you have an imbalance, it's always better to put the boreholes as far away as possible, make an open configuration, and also to think about the effective borehole thermal resistance. Make this as low as possible. And sometimes it's also better to increase the number of boreholes, where we have to make sure that we keep in mind that we have a laminar and turbulent transition zone that affects our effective borehole thermal resistance, and hence also the amount of imbalance we can cope with. But for some cases, for example, when we have injection dominated borefields and our maximum temperature is really critical after a couple of years, perhaps there is no other option than drilling more boreholes. And another option when you're extraction dominated is to go to drill deeper boreholes, because the ground is warmer. You're not changing your profile as such. You're changing it a little bit due to the G functions, but not that much. But you have a higher initial temperature, making it easier to cope with the temperature drift on the long term. So this was how to cope with imbalance. In the next part, we will be putting on another hat, namely that of the architect or the system designer. And we will talk about how we can avoid the imbalance. And this will be released next week on the 4th of November. And I'm looking forward to seeing you in that video. And if you thought it was interesting, consider subscribing so you don't miss out on that one. Share it with your colleagues. Try out GHC2 Cloud. You can schedule a free demo with me and we can discuss how it can be of benefit for your company, for your project. And I'm looking forward to seeing you in the next video. Take care. Bye.